In this short video, I'm going to show you how to describe a basic circuit using a netlist, which is a text description of a circuit topology, and it is used when um, basically capturing the description of a circuit for use in circuit simulation, particularly with SPICE, which is a circuit simulator that was developed by UC Berkeley back in the 70s. SPICE stands for Simulation Program with Integrated Circuit Emphasis. It's kind of cheesy sounding now, but people say SPICE, and you have to think for a while before you even remember what SPICE really stands for. But the main thing is that SPICE is a numerical software package that solves networks of or sets of nonlinear equations describing circuits. Now there are a number of different commercial products out there. Most of them have actually had their launching point from Berkeley SPICE. Berkeley SPICE is no longer being developed actively. I think it stopped maybe in the early 90s. The last version that was released was version 3F5. Some commercial programs actually used much older SPICE. So for instance, Cadence OrCAD PSpice, or just shortly PSpice, which we have installed on our university machines and which you will use sooner or later. It has its basis in SPICE 2G6, which is much older, and has some disadvantages that way just because it didn't benefit from all of the latest improvements. At any rate, what we're going to use today is called NGSPICE, and it's a browser-based version or instance of NGSPICE. NGSPICE is open source. It is based on 3 different programs. One of them is Berkeley SPICE, another one is called XSPICE, and a third one is called, I think, IceCube. Anyway, if you look it up, it will. You can find a description of it on Wikipedia. It's open source. It has all the power of SPICE, but it adds other capabilities as well, especially if you're doing event-driven type simulation, which would be the case for digital simulation, or maybe do some switching power circuits. At any rate, for our purposes, it doesn't really matter. You can just think of this as SPICE, and the reason that I'm pointing you to it is because it's super easy to use in that you do not have to install a program. You can just enter the text-based description of the circuit right here in this text box and then hit the simulation button and it gives you the results. So I'm going to demonstrate this by actually carrying out a couple simulations. We're going to begin with example 1A. And what you want to do when you go to describe a circuit using a netlist is you need to have all the nodes numbered, and then you need to have all the elements numbered as well, which of course I don't have here, but it's a small enough circuit that I'm just going to tell you verbally how I'm going to number them. The current source on the left, I3, or 3 amp source, I'm going to call I1. Current source on the right I'll call I2, and then the resistors from left to right I'm going to call R1, R2, and R3. The nodes, the bottom node here is the common or ground reference node. I'm going to call that 0, and then the node on the top left is 1, and the node on the top right is 2. So we're going to have an entry, a line for every element in our circuit. And then we'll have 1 or 2 command statements that will tell SPICE what we want it to do with that circuit netlist. So the first thing you always begin with is you have some title in the very first line. I'll just say example 1A circuit. And the first line is always ignored, so it's treated as a comment. Any comment that you add thereafter, you have to start the line with an asterisk. So this is a comment. Or if you want to put a comment at the end of the line, you can use a semicolon, which I'll show you in just a second. So let's begin by inputting our, let's start with the resistors. R1, okay? And the way you enter any element is you first give it a reference designator, in this case R1. SPICE knows what kind of element you're actually meaning to input by the first letter. So R is resistor, and then you could call it R apple, R23, R1, doesn't matter, but R is what tells SPICE that it is a resistor. Then we list which nodes it connects to, and we go from the positive node, which is 1 in this case, by my choice, and to node 0. Then we give it the value, which is 2 ohms. And that's it. I've placed spaces between here, and that's all you need, whether 1 space or 2 spaces or whatever, it doesn't matter. If I wanted to put a comment here, I would say node 1 is the positive node. Okay, what does that mean? Well, remember our passive sign convention says that the convention for voltages, branch voltages, and branch currents is that the branch current, a positive branch current, flows into a positive node. So, if I say R1 connects from a positive node 1 to a negative node 0, then if I were later to ask for what is the current flowing through R1, IR1, it would be the current that enters node 1 and flows to the resistor, or in other words, schematically, it's the current that flows downward from node 1 to node 0. Alright, let's do the second resistor. It's going to be R2. It's going from node 1 to node 2 as a value of 5. And then R3 goes from node 2 to node 0, value of 1. Then we have to specify our 2 current sources. I1, which is on the left, and it flows by the arrow indicated on the current source. It flows from 0 to node 1. So I'm going to go 0 to node 1, and it has a value of 3. And I can put A for amps. It ignores the A, but that's helpful in just reading the netlist. Incidentally, if it were milliamps, I could put M. If it was kiloamps, I could put K. If it was nanoamps, I could put N. If it was microamps, I'd put U. Femtoamps, F. It recognizes these things. But it only recognizes the first letter, and then it ignores everything else. And if it doesn't recognize it, like A, it just ignores it. Alright, we're done describing. No, we're not done. We got to put I2, and that goes from node 2 to node 0, and it has a current value of minus 2 amps. Now we're finished describing our circuit. The only thing we need to tell SPICE now is what we want it to do with that netlist. We want it to simulate what's called an operating point simulation. There are a number of kinds of simulation: DC, AC, transient, etc. But what we're doing right now, in other words, just trying to find out what is the DC voltage or current at every point in the circuit, we're just doing an operating point simulation. And then we have to put a .in statement. Okay, so now we are ready to simulate. And we'll go down here and just hit the simulate button. And the results show up right away. We have 2 results. We have just the node voltages for V1 and V2, which are found to be 5 and 2.5 volts. And now if we want the currents for the resistors, we can calculate those from the voltages. If you check the result for this problem, 5 volts and 2.5 volts is the correct answer. So now we're going to work another problem. Okay, we'll do example 2. Alright, and I'm just going to enter this in quickly, V1 on the left, and without much explanation, because now it should make good sense to you. R1 going from node 1 to node 2, it's 20 ohms. R2 going from node 2 to 0, that's 10 ohms. R3 going from node 2 to node 3, 15 ohms, and then the voltage source V2 going from node 3 to ground, 100 volts. And that is how fast you can enter the netlist. It's much faster than drawing a schematic when it's a small circuit like this. The results are, in this case, we have 3 voltages. V1, V2 is the unknown in the middle, because the V1 is 150 volts as we'd expect, V3 is 100 volts as we'd expect, and V2 is 65.4 volts. And then the currents, the other results that it provides in this case, because we have voltage sources, it will provide the current through the voltage source. So IV2 is found to be minus 2.3 amps. And the question is, which way is that current flowing? Well, by passive sign convention, because the positive terminal, let's go back up, the positive terminal of V1 is node 1. Remember, when you enter an element in the netlist, the positive terminal for that element is always listed first. So the positive terminal for V1 is node 1, and so a positive current, based on passive sign convention, means current that enters that node. In other words, it flows down into that source from node 1 to node 0. In other words, it is the negative of current I1, which is flowing counterclock or clockwise. So if I go to my solution here, I think I have a result. Yeah, so the result there is I1 is I1 is 4.23. Let's see if that's what we had. I1, yeah, it listed I2 for, so IV1 is minus 4.23. In other words, I1, our mesh current, is plus 4.23. I now want to show you an example that involves a dependent source. So let me first point you to some documentation. So on the NGSPICE page, there's a link for documentation. So let's go there for a moment. And there's good documentation. What I want to point out right now is we're going to go to the section that describes the elementary devices. One of those sections is voltage and current sources. One of the subsections is independent or dependent sources. So we're going to click on there. And what I want to show you is there's a lot of detail, but this very first paragraph with these lines here are essentially the only thing I need to reference when I forget the exact names of these type of control sources. Remember, I told you that in SPICE, the way SPICE recognizes a device is by the first letter in the netlist, or in the reference designator. So R for resistor, you know, I for current source, so forth. So the question is, if I have a dependent current source, what is it? Is it I? Or is it some other letter? It turns out it's a different letter. The way you remember which letter it is you can go to the online help here, and there are, as you already know, there are 4 different dependent sources. There are 2 types of sources, current sources and voltage sources, but then a dependent source says that that source, whether it's voltage or current output, is dependent on some other state in the circuit, which could be either a voltage or a current. So there are current and voltage outputs, and the controlling terminal or controlling signal for each of those could be voltage or current, meaning you get 4 permutations. So in our case here, we have what's called a voltage controlled current source. Why? Because the output is a current source. It produces current, but it's controlled by a voltage Vx. So it's a voltage controlled current source. VCCS, voltage controlled current source. So what letter do we use? Look here, between all of these, the first one outputs a current and it's based on a voltage. That's actually the one we want. The second one outputs a voltage and it's dependent on a voltage. Third one outputs a current dependent on the current. Last one is a voltage output dependent on a current. The scaling quantity here is, in the end, the dependent source is going to have a proportional relationship between what it produces at its output and the controlling variable. That proportional term is captured by these letters G, E, F, and H. In this context, they essentially are a number, but they also signify for us the letter that we will use for that type of device. So for a voltage-controlled current source, I want to use G. So let's go back and try this out. I'll go ahead and start with my dependent source, G1, or G whatever, and it goes from node 1 to node 3. And then now this is the part that I have to give you more instruction on. We need then to specify the controlling voltage. And the way we do that is we list the positive and negative nodes of that voltage. In this case it's Vx, and Vx by the schematic is shown to be the voltage between node 1 and 0. So I'm going to put 1, 0. All right? And then the last piece of information is, what is that scaling factor? What is the proportional relationship between the controlling signal and the output? In this case it's 0.1, so I type 0.1. All right? That's how you input a voltage controlled current source. Let's finish the rest of the circuit. I've got R1 that's going from 1 to 0, it's 10 ohms. I1 going from 0 to 2, and that's 10 amps. R2, I went out of order here, 1 to 2, and that's 5 ohms. R3 is going from 2 to 3, that's 10 ohms. And finally R4 going from 3 to 0, that's 5 ohms. And that is my circuit. So now let's simulate. And let's just check our result by looking at V2. So V2 is the third output here. It'd be 66.6 volts for V2. The other ones look to be 33. So let's scroll down here. Yeah, the answer is 66 for V2, as we see down here in the bottom right on this page. So that is correct. Let me show you one more example. Okay, finally we have example 6 that I want to show you, and the reason I want to show you this example is that there's another variant of a dependent source. So in this case we have, if you look at the source, you see that it's a voltage source, but it's dependent on what? It's dependent on a current Ix. So it is a current controlled voltage source. So let's look at the documentation again and note which one puts out a voltage that is dependent on a current. That is this guy over here. Puts out a voltage dependent on a current. So the element that we're going to use is H. Okay. So keep that in mind. Let's start at the left. I've got V1 going from 1 to 0, 150 volts. R1 going from 1 to 2, 20 ohms. R2 going from 2 to 0, 10 ohms. Let's go ahead and do V2 going from 3 to 0, 100 volts. And then now we have to put in our controlling source, H1, and it connects. The positive node is at node 3 to 2. And then we have to specify what is the current that it's dependent on. In this case, I don't specify 2 nodes. I actually specify a voltage source through which that current flows. All right, and if I recall, you couldn't say, well, let me just show you what we're going to put here. We're going to put V1 because Ix is current flowing through V1. All right, so that says the controlling signal for this current controlled voltage source is the current that flows through V1. And the sign convention, it uses the passive sign convention. So when I say V1, it means current flowing into its positive node, i.e. flowing from node 1 down through the source into node 0, which is precisely the orientation that we have depicted Ix as. The last piece of information we need now is what is the scaling factor, and that is 2. Now I should just mention that the controlling elements, or the elements that you can use for providing a controlling current, are voltage sources and inductors, but not resistors and not capacitors, if I recall. And what that means is, for instance, we could not have put in this case R1. I don't think it would have let us do that. It doesn't keep a variable of current for R1, as you noted in some of the other results. it'll always tell you the current through a voltage source, but it doesn't tell you the current through a resistor. It just gives you node voltages. So we would, if you did not have a voltage source in a circuit, in a branch, and it was that branch current that you wanted to use as your controlling current, what you'd have to do is actually add in a voltage source in series, say with a resistor, if that's what you were trying to, if that was the current you're trying to pick off. You'd put in a voltage source in series with it, and you'd give the voltage source a voltage value of 0 volts. So it wouldn't affect the circuit, but now it gives SPICE a voltage source that it can, from which it can grab a current, which it uses as the controlling current. Okay, so we are finished describing this. We're going to simulate. And we find that V2 is 104.5 volts. Let's see, did I solve this problem? Okay, let's look at the currents. The two currents here are 2.27 and minus 8.2. Let's see what we have here. Yeah, minus 2.27 and minus 8.2. And again, the reason that we have 2.27 amps and minus 2.27 amps is that in the hand solution, we are depicting this mesh current I1, which is flowing in a direction that's opposite to the current defined for the voltage source V1. And so that's why the signs are opposite, but these answers are in agreement. I should mention one last note. You might wonder in this, when you actually just load up NGSPICE for the or the ngspice.com the first time, you'll see some things in here like V1, V2, V3 in the plot window. The plot window will make more sense later when you're doing a different type of simulation, mainly a would be a DC, AC, or a transient simulation. So that's useful, but for right now, when we're just doing operating point simulation, the only output are these singular numbers that are associated with different branch currents and node voltages.